Hey guys, Professor Brown here, and today we're going to do the calorimetry experiment. To do the calorimetry experiment, you're going to want to have on hand some hot water, ideally about 80 degrees Celsius. You're going to want to have some room temperature water. You're going to want to have something to handle the hot water with. You're going to need a 50 milliliter graduated cylinder. You're going to need your calorimeter apparatus. I'll say more about that in just a moment. You're going to need the ammonium chloride from the kit, the calcium chloride from the kit, the electronic balance, and something to weigh your ammonium and calcium chloride on. I have some weigh boats. You may want to use the pans in the kit or some aluminum foil from your house. At the end of the calorimetry experiment, we are going to try to experimentally determine what we call the enthalpies of solvation for calcium chloride and ammonium chloride. And we're going to compare them to the accepted literature values for those substances and see how close we get. So calorimetry is a method that chemists use to measure the energy changes associated with chemical and physical processes. Today we're going to measure the energy change associated with the dissolving of ammonium chloride and calcium chloride in water. We can also use calorimetry to measure the energy changes of any substance combusting, or many other types of chemical reactions that we could think of. Calorimetry is done in what we call a calorimeter. And what calorimeters do is they are instruments that are designed to isolate a process, a system, a chemical reaction, or a physical process from its outside environment. We want to minimize any energy exchange between the system we're trying to measure and the outside of the environment. And that can be kind of tough, considering heat energy is always kind of in motion around us, moving from hotter positions to colder positions. And so calorimeters are designed in such a way they're insulated to hopefully mitigate most of the energy transfer between a system and its surroundings, so that we can accurately measure how much energy is being moved in that process. Lab-style calorimeters are these nice big insulated boxes that contain a vessel inside that holds a bunch of water, and a smaller vessel fits down inside of that water bath, and that's where the process is carried out. And it's really sealed up around all of those sides, except for some thermometers that are poked down into the water. And the measure of the temperature change of the water allows us to know how much energy was taken or removed from that process. This is the way that we actually measure the energy content of our food. When you're eating some kind of packaged food and you turn it over and you see it has X amount of calories, what was done is a standardized amount of that food was taken and placed into a calorimeter like you see here. It's placed in this inner chamber here, and then it's actually combusted, it's burned, and the amount of heat that's produced from that amount of food heats up the water surrounding it. We measure the temperature change of that water, and we equate that to some amount of energy, and that energy is reported as calories on that food packaging. We are going to use, as we've already said, the coffee cup calorimeter. The way I made this was to take my 250 milliliter beaker and place 2 styrofoam coffee cups down inside. I took a third styrofoam coffee cup and cut out just below the first ring there and stuck my thermometer through the middle, and now I've got a nice little cover for my calorimeter so that I can isolate the water that I'm going to dissolve my salts in. So, like I said, we're going to try to measure the enthalpy of solvation for ammonium chloride and calcium chloride. The dissolving process is generally looked at in 2 separate steps by chemists. In the first step that we see diagrammed here for sodium chloride, regular table salt being dissolved, this is analogous to calcium chloride and ammonium chloride as well. In the first step, the ions first have to be broken apart from each other. And that always takes some amount of energy. In the case of sodium chloride, to break apart 1 mole of sodium ion and chlorine ion pairs, then we need to input 778 kilojoules of energy. Then in the second step of dissolving, water molecules surround and stabilize those ions. And there's always a release of energy during that process because of that stabilization from the water molecules. In the case of sodium chloride, 774 kilojoules per mole of that energy is released. That means there is a difference of 4 kilojoules per mole between these two processes. So every time 1 mole of salt, regular table salt, dissolves in water, it has to get that 4 kilojoules per mole, and it gets it from its surroundings. So typically it draws 4 kilojoules of energy in from the water. And what that means is the temperature of the water goes down. And so we call that process endothermic. Now, it's not really that noticeable with regular table salt. If you dissolve a bunch of salt in water, the water will cool down, but it's not quite as noticeable. The one that we use today that's endothermic is quite noticeable. You might be surprised at how much colder the water gets when this salt dissolves. On the other hand, one of our salts today is also exothermic. So what that means is a lot less energy is needed to bust apart the molecules than is released by the stabilization of the water molecules. And so overall, we have a net negative enthalpy change associated with that salt. And when we dissolve that salt in water, because that energy is released, because it's net negative and it's going out into the system, that means that that water is actually going to get a good deal warmer when that salt dissolves. All right, in the first part of the experiment, we're actually going to determine a fudge factor for our energy that we lose to the calorimeter. You see, even though these work pretty well, there is a known bit of energy loss between the system we're trying to measure and the cup and the surroundings that is surrounding it. And so when we do our enthalpy of solvation, we would like to be able to account for that energy transfer. So we're going to figure out, on average, how much energy is lost to that calorimeter during our measurements. To do the first part, you're going to need to get 50 milliliters of the room temperature water, measured using the 50 milliliter graduated cylinder. Make sure you put the meniscus exactly on 50 milliliters. I've got just a little too much there. Yeah, that's better. And transfer that 50 milliliters of room temperature water to your calorimeter. You'll see that I've taken the cap off. I'm actually not going to use it because I'm not able to see the temperatures on these smaller thermometers. You may be able to use the cap if you have one of the bigger thermometers, but with the small ones, we'll just have to leave it off. We're accounting for the energy loss anyway, so it's not that big of a deal if you don't end up using the cap. Take your thermometer, swirl it around in there a few times, and get the temperature of the room temperature water, and that's going to be the initial temperature of the cold water in each of your trials. So I will wait for my thermometer to equilibrate nicely. And it looks like my cold water, or my room temperature water, is about 24 degrees Celsius. Then you are going to want to get a stopwatch ready and prepare your hot water. So you're going to take your hot water and pour about 50 milliliters, or not about, exactly 50 milliliters of the hot water in your graduated cylinder. Going to take your thermometer and put it in the hot water and determine the temperature of the hot water before you do anything else. Let the thermometer stop rising before you take the temperature reading. my hot water is about 77 degrees Celsius. So you'll write that down, 77 degrees Celsius, and then you're going to want to pour the hot water into the cold water, insert the thermometer, and start a stopwatch at about all the same time. Hot water, start the stopwatch, maybe give it a swirl, and then lay the thermometer down. And what you're going to do is you're going to take temperature readings of that water every minute for 10 minutes. You wait for the first minute to pass before you take your first reading. So I will put my stopwatch there. And wait for the first minute to go by. And after the first minute, my water is at 50 degrees Celsius. And I will take 9 more readings at every minute until 10 minutes. At 2 minutes, my temperature has dropped to 49 degrees Celsius. And I'm done. So we're going to use Excel in order to find one of the figures on data table 2 using the information that we generated on data table 1. You can see that I've already outlined my 2 columns here. In the first column, A, I want to put 1 through 10 to represent each temperature of the water after we mixed it. Then in column B, the second column, I'm going to put those temperatures that at each minute. I'm going to have time on the x-axis and temperature on the y-axis. I'm going to highlight my data and insert a scatter chart as always. And on this scatter chart, I am going to add my trend line, and I am going to display the equation on the chart. Now, real important here, do not set the intercept on this graph. The intercept, the y-intercept, is this figure right here in our formula for the line. That tells us where our line will cross the y-axis. And because time is the x-axis, the y-axis sits at the 0 minute. We are interested in what the temperature of that water was right when we put it together. And our thermometers have a little bit of a lag in them, so we can't trust them to measure right away. So we set this data up and then extrapolate by looking at where it crosses the y-axis, and that would be that number there. So that is the temperature of the water at time 0, right when we mix them together. That figure will go on the data table 2 under temperature at time 0. Now that I have determined from my calibration curve that the temperature at time 0 from the graph is 50.3 degrees Celsius, I can fill in the rest of the information on my table. The row above the temperature at time 0 asks for the average temperature. To find the average temperature, you just add the initial temperature of the hot water to the initial temperature of the cold water and divide by 2.
And quite frankly, I don't know why they asked for that figure because we don't use it in the calculations, but it's there, so we will do it. The average temperature of my mixture was 50.5 degrees Celsius. We can see there's a little bit of variation. The temperature at time zero from my graph is 50.3 degrees Celsius. Now we want to know how much heat was lost by the water to the calorimeter. And to do that, we need to figure out how much heat the hot water or how much heat energy the hot water gave to the cold water and see how much of that energy the cold water absorbed.
Now we're ready to do part 2 of the experiment. In part 2, we are going to dissolve the calcium chloride and ammonium chloride in 100 milliliters of water and determine how much temperature change takes place during the dissolving process. So what you're going to want to do is grab your 50 milliliter graduated cylinder again, and we are going to put 2 50 milliliter portions of room temperature water into our calorimeter for a total of 100 milliliters of water. Now the first row on your data table here asks the amount of mass of water that we put in our calorimeter. And we should keep in mind that water has a density of 1 gram per milliliter in order to determine what mass in grams of water we're using. So we put our 100 milliliters of water into our calorimeter and put our thermometer in as well. And then we are going to measure out. The first column says to do 5 grams of calcium chloride. So I'm going to put my weighing implement up on the balance, and I'm going to hit the tare button. And then I'm going to take the calcium chloride and open it up and dump a little bit into my weigh boat until I'm somewhere close to 5 grams. Now you don't have to get exactly 5 grams because we are going to write down the exact amount that we do use. For instance, my balance right now says 5.16 grams, so I will write 5.16 in the mass of salt column. The next column, or the next row, asks for the moles of salt, and you can figure that out using the molar mass of the salt. The next row asks for the initial temperature. So the initial temperature is whatever temperature your room temperature water is sitting at. My room temperature water is 23 degrees Celsius. So I will write 23 degrees Celsius there in that row. The final temperature comes after you dissolve the salt in your 100 milliliters of water. So now you're ready to take your salt sample and try to do this rather efficiently. Dump all of the salt into the water. And give it a good mix, ideally with a spoon and not the thermometer. And observe the temperature change. So what you're going to do is one of these salts is going to increase the water's temperature and one of these salts is going to decrease the water's temperature. You are going to want to wait until that increase or decrease has stopped. Wherever the temperature levels out at, that's what you want to write down as final temperature. So give it a few minutes and make sure my thermometer is right now at 31 degrees. I'll give it another 10 or 15 seconds, and if it's still at 31 degrees, I can write 31 degrees down as my final temperature for my first trial of calcium chloride. It is still at 31 degrees Celsius, so I feel like that is a good final temperature for calcium chloride. So the process is the same for the next 6 columns. You do vary the amount of salt that we use every time. In the first trial, we used 5 grams. In the second trial, we're going to use somewhere close to 10 grams.
My video was cut a little short there at the end, but all I was saying is we were going to do that procedure 6 times. We're going to vary our amount of salt every time. We will do 5, 10, and 15 grams of calcium chloride, and we'll also do 5, 10, and 15 gram samples of ammonium chloride. And we are going to now fill out one of the columns. The first row asks for the mass of the water. Since we used 100 milliliters of water, we therefore used 100 grams of water, since water has a density of 1 gram per milliliter. We see the moles of salt in the next row, the mass of salt in the next row, which we wrote down from our balance as we were experimenting. And the next row asks to convert that mass to moles, and we do that via the molar mass. 5.16 grams of calcium chloride times 1 mole of calcium chloride for 110.98 grams of calcium chloride, determined by adding up the atomic masses from the periodic table of calcium and 2 chlorine atoms. Then we see that we divide our mass by our molar mass. 5.16 divided by 110.98 is about 0.46 moles. 0.46 moles of calcium chloride used in that trial. The next 2 rows, the initial temperature and the final temperature, were measured during the course of the experiment. And the row after that asks for the change in that temperature. To find the delta T, or change in temperature, we do the final temperature minus the initial temperature, or in my case, 31 minus 23 equals 8 degrees Celsius. So the change there was 8 degrees Celsius. Then we want to know, well, how much heat was absorbed by our water? And the formula for that is the Q of the water is equal to the negative of the specific heat, CW, of water times the mass times the change in temperature. So in this case, it's going to be the negative of 4.18 is the specific heat of water, times the mass was 100 grams of water, times the change in temperature was 8 degrees Celsius. That all comes out to negative 3,344 joules. The next row is the heat. We are just going to write down the heat capacity of the calorimeter. That is the value that you arrived at in data table 1. You should use your average, but seeing as how I only did one trial, I'm going to use the one figure that I came up with. That was 3.18 joules per degree Celsius. So now we can figure out how much energy our calorimeter absorbed while we were doing this experiment. So we will take the negative of the heat capacity of the calorimeter times the change in temperature. So in this case, Q of the calorimeter is equal to the negative of 3.18 times the change in temperature, which was 8 degrees Celsius. 3.18 times 8 is 25.44, so the answer is negative 25.44 joules. Now we will find the enthalpy of the solution by adding the Q of the solution and the Q of the calorimeter. So these two numbers here, this one and this one. negative 3344, negative 3344 plus negative 25.44 equals negative 3369.44 joules. And we can see that is in joules, and we want that to be in kilojoules for the next row. Which is simply dividing by 1,000 or moving our decimal place to the left 3 times. So that would be negative 3.37 after rounding kilojoules. And then the final row down there asks for the enthalpy per mole of solution. So kilojoules per mole. So we will divide this number that we have here by the moles of salt that we used here. So in that case, the negative 3.37 divided by 0.046 arrives at an answer of negative 73.3 kilojoules per mole. I'm writing my unit underneath. Kilojoules per mole. Now, there is one more box to fill in down here, but that is an average, so I would need to do all 6 of, or at least all 3 of the calcium chloride trials to average the calcium chloride. So to answer this box here, you will average these 3 figures, add them all up and divide by 3. To answer this box here, you will need to average these 3 figures, add them all up and divide by 3. One last piece. On question 4 of the post lab, you're going to be asked to solve some problems using an equation that you determine from your data of temperature change versus mass used of each salt in 100 milliliters of water. So what you're going to want to do is you are going to want to make a graph of the data from the calcium chloride and the ammonium chloride. So you should do 2 of these, one for calcium chloride. I will show you the calcium chloride, an example using my calcium chloride. So in my first trial, I used 5.16 grams of calcium chloride and my temperature change was about 8 degrees Celsius. In the second trial, which you guys didn't see, I used 10.3 grams of calcium chloride and I got a temperature change of about 18 degrees Celsius. And in my fourth trial, I had a mass of about 15.12 grams of calcium chloride and I had a temperature change of about 23 degrees Celsius. So I will take that data and insert a scatter plot and get me an equation for that line. And turn on the trend line and give my equation there as well. And we can see that the temperature change is the y-axis and the mass of salt used is on the x-axis. And so that equation allows me to answer those questions in 4 and beyond on the lab. If I want to know what mass will give me a certain temperature change, then I would plug that temperature change in for y and solve for x. If I want to know what temperature change mass would give me, I would plug that mass in for x and solve for y.